All right, hello AP students. Welcome to your AP problem walkthrough on electrochemistry cells and the Nernst equation, which is used for non-standard conditions of an electrochemical cell. We're going to go over three conceptuals, just sub-question A in each section, and then hit up a short FRQ. So, of course, look in the description for the timestamp of when the AP question starts. However, I do think the conceptual is very useful, especially considering this is the last unit and all of us, our brains are tired and we need to go over things a little bit extra. So that being said, if you go to question number 13 in your workbook, we have determined the standard cell potential in volts for each of the following combinations of half cells, show the electronically balanced half reactions and the overall net reaction. So this has to do with interpreting this unique format of writing electrochemical cell setup. And what we see here is that for this, you need to recall that we always represent with the double line. Here we have, this is the half cell separation, right? These are half cell separations. And for our first half cell, we always tend to write the anode first, which is, by the way, the site of oxidation. So you know that you're going to be losing electrons. And that makes sense given that your anode, okay, relationship demonstrated here is going from solid aluminum and to aluminum 3 plus, very much aqueous, and therefore losing 3 electrons. When you look at the other half cell after the 2-line divide, according to this notation, we see that we are looking at the cathode, which is always the site of reduction. And so you know you're going to gain the electrons. So for here, we see, again, reading from left to right, we see copper 2 plus aqueous, gaining 2 electrons to go to copper solid, which of course has a 0 charge. Now, as far as balancing the half reactions, we need to realize that we have to electronically cancel. All right. So what we would say is that we need to multiply the aluminum half reaction by 2 and the copper half reaction by 3. All right. So that would result in a sum of my electrons would cancel from reactant and product side. The amount that I lose in aluminum is the amount that I lose in aluminum is gained by the copper below. And what I get is 2 aluminum solids and 3 copper 2 plus aqueous ions react in a redox and transfer 6 total electrons between the two of them, a transfer of 6 electrons to produce aluminum 3 plus aqueous in some type of compound and copper solid. And that would be the sum overall net balance reaction. And that is electronically balanced. And then we're asked to also determine the cell potential for this redox. So according to the half reactions, you would have to look at your standard reduction potential table. All right. And you would have to go in and find these values. So if you go to your notes, our standard reduction potential table is here, and where we see aluminum. Okay, let's find aluminum first. And it is undergoing oxidation. So you need to look for it on the right side. And I'm not looking in the right places, apparently. Aluminum solid to aluminum 3 plus. So we see aluminum is on the right side of the table, which means we are now looking at the reverse direction, which is the oxidation direction. And we would say it has a negative 1.66, okay, volt. But remember, that's for reduction. So because this is the oxidation direction, we will flip that value. And we will say that the E naught, okay, for this oxidation is positive 1.66 volts. And then we again look at the reduction potential on the table for copper and copper 2 plus, I should say. And we see that for copper 2 plus reduction, we would be now looking on the left side. And we see that copper 2 plus going to solid copper is apparently escaping my vision. Here it is. is positive 0.34, and we do not have to flip the reduction potential value because we are looking at copper from the viewpoint of it being reduced, which is how the table is written. It's reduction potential. So if you read from the oxidation end, you have to flip the value. And so we would say it's positive 0.34 volts. Okay. And we do not multiply. Okay. Remember, this is an intrinsic property. So we do not multiply by 2 or 3 for these values because the reduction potential doesn't change depending on how many moles of the reaction you have. It's still the same reduction potential. So then you just sum this up and you get a value for this overall cell potential is 2 volts. All right. So that's kind of your first walkthrough. Let's go ahead now and look at question number 14, where you are now looking at non-standard cell conditions and you're required to use the Nernst equation. So for the Nernst equation, what you have to keep in mind is this is one provided to you on the equation sheet. And the standard Nernst equation is E of the cell and under non-standard state conditions is equal to E of the cell under standard state conditions minus RT all over NF Faraday's constant, ln(Q), okay? Ratio of products over reactants. So what we would say here is that we are given the following reactions, and it's at 32 degrees Celsius in temperature. In order for us to work with the correct R value, which the R value that we will be working with is 8.314 times joules per moles Kelvin. Okay, we need that degrees Celsius turned into Kelvin. So we're going to do 32 plus 273.15. And that's going to get us a value of 305.15 Kelvin. All right. And all we simply do is now plug and chug to figure out the cell potential of this non-standard state conditions galvanic cell. And we see that this is equal to, well, we need to figure out the sum of the cell. So we have the electron potential of the standard condition cell is negative. Ooh, which one's the better reducer? So we say this one is going to undergo reduction better because it's more positive. So we would say then that it'll be, we're going to make this the oxidation because it's a worse, or I could put it like this, it's less likely to be reduced because of its negative reduction potential value. So we're actually going to flip this and say that it will serve as the oxidation role, and therefore the E naught for this particular half reaction will be positive 0.403. Okay, positive 0.403. And what we will get then is that the E cell for the entire thing is 0.403 plus negative 0.126, okay, minus RT, and R is 8 I'll just color code just to differentiate, 8.314 joules per moles Kelvin, okay, times temperature, which is 305.15 Kelvin, all over the moles of electrons, that's your N, being transferred. So we have 2 moles of electrons being transferred between these reactions. And then we have F, which is Faraday's law. So we're going to plug that in, which is according to your AP equation sheet, 96,485 coulombs per mole. And by the way, a coulomb is equal to a joule over a volt. So, and you can find that on your equation sheet. So I'm going to say instead of writing coulombs per mole, I am just going to write joules per volt times mole, okay, times the ln Q, all right? And Q is what we get as a product over a reactant. So let me move this over because I clearly did not leave enough room. Okay, there we go. ln, and here, because we made our oxidation flip, we really have CD goes to CD2 plus. So the concentration of our CD2 plus is our product concentration that goes on top, lnQ. So we do products, which is 0.02 molar all over, okay, our reactant. And because that is the half reaction that serves a reduction, it's on the reactant side, PB2 plus 0.200 molar. And what you would do is plug that into your calculator, which give me a second to actually grab mine. All right, so I grabbed my calculator and I just simplified this down to the E naughts of this cell under standard state conditions would be 0.277 minus that whole kind of multiplication fraction right there. That whole constant would be 0.01315 volts. If you cancel out your units, you'd be left with volts, times negative 2.303 when you do the natural log of the respective concentrations of our product and reactant cations. And then you simplify that even more, and you get that the value of this is 0.1315, okay, times the negative number times -1, and you get that this is plus 0.277, and you get that the overall E of the cell under non-standard state conditions is equal to 0.307 volts. Okay, so it's just like a lot of button pushing, but you have B, you can do that on your own for practice. And then let's move on to question. This was actually question now 15 because I did some rearranging of the workbook. And question 15 now asks us to use the Nernst equation. And this time we're actually going to assume here for this one, we are going to assume that we are under 25 degrees Celsius conditions, which I realize now I probably should have written in 25 degrees Celsius. I think I did on the updated version. We're at 25 degrees Celsius. So when we're at 25 degrees Celsius, we actually get a logarithmic derived version of the Nernst equation that is not, I repeat, not provided on the AP exam, but is for some reason commonly discussed in practice problems. And that is that the E cell under non-standard state conditions is equal to E naught of the cell minus 0.0592 over the moles of electrons transferred log Q. And this is just a log derivation of the original Nernst equation, realizing that we are at 25 degrees Celsius or room temp, okay, or 298 Kelvin, right? Or 298 Kelvin. So this is just like a very specific version of the Nernst equation. And here we're asked to determine the E cell potential given the following. And so what you'd have to do first and foremost is actually write out the half reactions occurring between zinc and nickel. You'd have to look at your reduction SRP, reduction potential, and realize that zinc, all right, when you look at zinc and nickel, you would see that zinc is going to be the oxidized species because it is less, okay, it is less likely to be reduced, so it will serve as the oxidation, whereas nickel will serve as the reduction. So let's go ahead and look at that on the table. When we look at the table, we see that nickel, as far as, let's see, nickel versus zinc. Might be down here. So we see here nickel is found 2+ is found with an electron, oh my God, a standard reduction potential, sorry, not electrochemical cell potential. It has the same symbol, but it's different. The standard reduction potential of -0.26, whereas zinc, on the other hand, 2+, is below it with a reduction potential of negative 0.76. So we know that we're actually going to flip the reaction for zinc, and we're going to say that zinc solid acts as the oxidation role for this particular electrochemical cell, and nickel will stay as the actual reduction half of this electrochemical cell. So then when we say that, we would find that we would write our half reactions, okay? Oops, we'd write our half reactions and we would say, well, nickel is gonna serve as the reduction half, and that half reaction is the following, going to nickel solid, giving us an E naught of negative 0.26 volts, whereas the zinc 2 plus, we're actually going to say it's going to undergo oxidation. So we're going to flip that reaction producing zinc 2 plus. So it'll be zinc solid goes to zinc 2 plus and it produces 2 electrons. And that E naught is going to be the flip of what we see on the table. So it's going to be positive 0.76 volts. And that would give us an E naught of, for the cell, of positive 0.50 volts. And then what we do is we take this, and I definitely wrote too big. We take this and we plug into our derived Nernst equation, which is E of the non-standard cell is equal to E naught minus 0.0592 all over the moles of electron transferred log Q. And we get that that is equal to 0.50 volts minus 0.0592 all over 2 electrons, right? 2 moles of electrons times log of Q. And here Q is, we're told that we have a concentration of, geoliters. We have a concentration of 5 moles per liter from 1 moles per liter. So we're going to say that by the addition to increase 200 from 5 moles per liter to 1, we're going to do a ratio and say that the concentration of zinc is going to be on top because it's our product. Okay, all over the reactant nickel 2 plus. And that will then simplify down to 0.50 volts minus 0.0592 all over 2 moles log of 1 molar all over 5 molar. Okay. And the reason I can say that the 5 molar is representative of the concentration of nickel is because nickel is the reactant. And if we're going from a concentration of ions that goes from 5 to 1, then the new ion in solution is now the zinc 2 plus, which is our product. So therefore the 1 molar must be the zinc 2 plus concentration. And we get that this is equal to an electrochemical potential of 0.52 volts. Okay. So those are your conceptual. Now let's go through the AP short FRQ. And if you scroll all the way down, it's question number 4, short FRQ. And what we have here is we have a standard galvanic cell. Again, we're under standard conditions. We're even given the half reaction values and the E naught, but notice we're giving them totally in terms of reduction. So you know automatically that you're going to be flipping some signs. Okay. And we're given a diagram of how the half cells are set up, and we're asked to write the overall net reaction for this. So what you need to keep in mind is that you need to only be concerned at this level about the electronic balance. I'm not telling you if you're an acidic or basic. Like I said before in lecture, it's really not a common question to be asked about that. It might be consideration in a prompt, but very rarely are you ever really asked to balance for an acidic or basic. It's just a conceptual thing that we walk you through, that those are scenarios you have to account for. But here we don't need to. So what you do is to write the net reaction, you need to identify what are your reduction and what are your oxidation halves. So what we're looking here, who's going to be the best reduction, who's going to be the most likely reduced, and that will of course be copper 2 plus. So what we're going to see here is we're going to actually have to flip this one, and we're going to see that zinc acts as the oxidation role. So you're going to definitely turn this from a negative to a positive reduction potential. And you're going to flip-diddy dip this half reaction. Okay, and that's my reminder. So then what would be the net ionic equation? Well, you would write that it'd be copper 2 plus, okay, gains 2 electrons to produce copper solid, and that zinc solid loses 2 electrons to create zinc 2 plus. And I totally wrote my Z as 2, zinc 2 plus. And then you sum this up. It is already electronically balanced because we have a 2 and 2 gain for every 2 loss. So that's kind of nice. And we get that our overall net reaction that is electronically balanced is copper 2 plus, most likely aqueous, right? Because we're working with ions here. Reacts with a zinc solid to produce copper solid and zinc 2 plus aqueous. Now we're asked to calculate the E naught for the cell. And so what we do is I will have accounted for the oxidation flipping. So I just simply add my values 0.314 plus positive 0.76. Okay. And I get that I have an overall volt potential, cell potential in volts of 1.10 volts. Heyo, this is like the dream FRQ. Okay, even for someone like me who is not physics inclined. And now we're asked to calculate the G for this. So you're going to want to use a new derivation that accounts for Faraday's law with electrochemical cells. And this is like another derivation of the Nernst equation, which is totally also provided on your equation sheet. And that is G for this reaction is equal to negative N, the moles of electrons transferred times Faraday's law times the electropotential of the cell under standard state conditions. And so what you would do is here you've found pretty much all the information you need. So you know that this is going to be equal to negative 2 moles of electrons times Faraday's law, which is 96,485 joules per volts times mole, because that's a joules per volts is equal to a coulomb. Joules per volts is equal to a coulomb. Capital C, I believe, is what I can just write. So that is also provided to you on your equation sheet. And times the electrochemical cell potential that I just solved above in part B, which is 1.10 volts. And I get that my value is going to be equal to negative 212,000 joules per moles of reaction. And here I want to report in kilojoules. So I'm just going to divide by 1,000. I get negative 212 kilojoules per mole of reaction. And then finally for D, what you're asked to do is you are asked to follow the diagram on the left represents the copper nitrate solution in the half cell before galvanic cell starts to operate. In the following diagram on the right, so your responsibility, draw a representation of the solution in the same half cell after the galvanic cell has been operating for some time and is producing a voltage. Pay attention to the amount of particles in charge. So what you want to account for is you want to make sure that whatever you draw is consistent with the half reaction that you determined above to be true. And what you should be looking for, let me kind of think this through. You should be creating a diagram where your Cu2 plus, okay, is being consumed. So you have less Cu2 plus after the cell running. So let's say I'm going to create Cu2 plus, okay, and I'm only going to have maybe 2 of them. Copy, okay, to represent that I've lost some Cu2 plus. In addition, you want to recognize this. Where is this NO3 coming? Well, the NO3 is being provided by the salt bridge. Okay, so the NO3 is, remember, we have to shoot ions, okay, into solution to create the continual flow of electrons by always making sure that the solutions, these specific metals that we're working with, are neutral so that electron transfer is promotable. And so what we see is we have a ton of NO3 in solution, okay? And we have to make sure that when the cell is running, we are keeping a neutral solution. And so we want to make sure that our NO3 amount, all right, is equivalent. So if we have NO3, okay, we want to make sure they cancel out with our Cu2 plus. So for every one Cu2 plus in solution, we need 2 NO3s to keep the overall half cell solution neutral. So I'm actually just going to copy and paste this one. Copy, paste, paste. And that means I need 4 NO3 minus nitrate ions to neutralize the solution. So that would be after the cell has run. I have now deposited and created some Cu solid copper, so I'm going to have less copper 2 plus aqueous in solution, and therefore less NO3 minus to keep the overall charge canceling true. So you could have done it with less. You could have done it with 1 Cu2 plus. Okay, you could have even done it with 3 Cu2 plus. Just make sure your NO3s cancel out, creating a neutral solution. All right, guys, really good job. And we're wrapping up. We're getting super close. Have a good one.